His constants are never arbitrary. When he divides by 0, he creates a brand new number. He once integrated by parts, and the parts apologized. He is the most interesting integral in the world. Also known as the most viral integral on the Math Stack Exchange, this is the integral we'll be tackling today. What makes this integral so challenging? Well, there's no obvious substitution, and integration by parts does not seem to simplify anything. The logarithm presents a formidable obstacle, and nothing suggests what the final answer should look like. Every standard method seems local. Every technique tries to manipulate this integral. What if this isn't the integral we are supposed to solve? Instead, what if we're supposed to study how this integral changes? Step 1 will be to employ Feynman's trick of differentiating under the integral sign. So we introduce a new parameter a to create a family of integral functions I of a. But where should we introduce this parameter? Well, in order to address the logarithm in the room, we will want to apply the new parameter a to that part of the integrand, and noticing a little symmetry within the argument of the logarithm, we will introduce the new parameter in the following way into the logarithmic function. Now observe that I of 2 is equal to I, and I of 0 is equal to 0, so that by the fundamental theorem of calculus, we get this result, creating the integral from 0 to 2 of I prime of a. So our goal will be to find I prime of a. Now differentiating under the integral sign with respect to our new parameter a will help us eliminate that pesky in the logarithm. So the partial derivative with respect to a of that logarithmic function gives us this rational function. And this yields a new I prime integral. One notices that the rational function that resulted from this differentiation can be decomposed into partial fractions. And this is the resulting partial fraction decomposition. So now we have this integral for I prime. And if we observe that f of x sub a is equal to this part of the integrand, we notice that it is an even function. That is, this function exhibits y-axis symmetry. It remains unchanged under x changing to negative x. So by making that substitution, we get the following result. I prime has this representation under that substitution. So what do you think we should do with these two representations of I prime? If your intuition told you to try adding them together, then I like the way you think. So now here is the result, or I prime is equal to this integral. Or in expanded form, this integral, which suggests we split it into two integrals. Let's let I prime be equal to two integrals, j plus k, shown here. And we'll examine the integral k first, which is this integral. Under a substitution of x going to negative x, the integral k transforms into the integral j, and therefore I prime is just simply equal to 2 times j, or 2 times this integral. Where do we go from here? Our attention is now drawn to the square root in the denominator. What kind of substitution would be useful for a radicand of the form 1 minus x squared? Think about it. If you were thinking about a trigonometric substitution, then we can be friends. Letting x equal cosine of theta, we get negative d theta to be equal to this expression, and working through the limits of integration, we get the following expression. I prime of a is now equal to this integral. What are your thoughts now? How should we proceed? It would be nicer if this integrand were a rational function instead of a trigonometric one. And to make the desired integrand back into a rational function, we will use a method popularized by Karl Weierstrass, by letting t equal the tangent of theta over 2, which will reveal cosine to be equal this, and d theta equal to this. And therefore our I prime becomes this. We're making progress, but where do we go from here? You were going to say normalize the quartic, right? Well, to normalize this quartic, we will rescale our variable by letting s equal the fourth root of this quantity, and therefore t equal to s times u. By that substitution, we got our denominator to be equal to this quantity. And b here is equal to negative 2 over root 9 minus a squared. And this yields I prime to be equal to this integral, a much nicer formulation. So if you've come this far, you're probably willing to go a little further. Where should we go from here? What is the integrand suggesting to you? If you were thinking to split the integral into 2, well, then we've gotten to know each other pretty well. So separating this integral into 2, and letting each of those integrals be L and M respectively, we have this expression for I prime. Like before, our instinct here is to examine the integral M. Here we're going to employ an inversion transformation by letting u go to 1 over u. And by that measure, we get m to be equal to this integral. Look familiar? Therefore, L is equal to m. those two integrals are equivalent. I prime can then therefore be written as follows. And by adding these two integrals together, we get the following integral. And now here's where a little trick comes into play. A pro gamer move. Divide both the numerator and denominator by u squared. (2m) then becomes this integral, and of course simplifying the integrand, we get this integral. And at first it looks like we've made a mess, but the integral suggests a substitution, one that is not quite obvious. Observe that if y is equal to u minus 1 over u, then dy is equal to 1 plus u squared, 1 plus 1 over u squared du. Then we can play around with this expression and reformulate the denominator of our integral to be as follows. Thus, we can rewrite our integral as this. For now, let's let c equal the square root of b plus 2, giving us this integral. And then we can rescale our integral by letting y go to cy, and that'll give us, ultimately, m is equal to this integral. And this one should look familiar to you. It's an arctan integral. And our final result is m is equal to pi over 2c, or pi over 2 square root of b plus 2. Now our integral I prime of a can be written in this way. Again, where m was the integral that equals pi over 2 square root of b plus 2. We can also rewrite this integral in the following way, which at first glance does look a little bit more complicated. So it calls for a little simplification. Recall that s is equal to this quantity, and let's make the substitution that r is equal to the square root of 9 minus a squared. Then r squared is equal to this factorization, 3 plus a plus times 3 minus a, and s squared can be written as follows. And then s can be written in a simpler way as the root of 3 plus a over r. S squared then is 3 plus a over r, and 1 plus s squared can be written as follows, putting our final integrand into this form. But observe that the square of r plus 3 plus a is given here, so that we might write r plus 3 plus a as a square root of this quantity. We can now put this all together into this quantity, and of course with some simplification we arrive at 1 over r times the square root of 2 r plus 3 all over r. Simplifying the radicand in the denominator for I prime, the square root of 2 minus 2 over r, we get this quantity. So I prime, putting those two square roots together, gives us 2 pi over r times the square root of r plus 3 over r minus 1. So there's one more thing here. The square root of 3 plus r over r minus 1 can be simplified down to a over the square root of r minus 3 times r minus 1. And so, we can get our integrand to look as follows. So to find I, or I of 2 here, we find ourselves with another integrand involving a square root. So what do you think our next move should be? That's right, baby, another trig substitution. Let r equal 2 plus cosine beta. So r minus 2 is equal to cosine beta, dr is equal to negative sine beta d beta, and the arc cosine of r minus 2 is equal to beta. Also, check that the square root of this quantity is equal to the sine of beta as well. And therefore our limits of integration become 0 to the arc cosine of the square root of 5 minus 2. Our integrand simplifies dramatically, and I winds up equaling 2 pi times the arc cosine of the square root of 5 minus 2. A little anticlimactic, but we are not done yet. You see, one can't help notice that the argument involves the square root of 5. This is a hint at something possibly golden. And so, using an half-angle identity shown here, with z equal to the square root of 5 minus 2, we get the following result. Two times the arctan of this square root involving other square roots, which can be simplified to this expression. And with further simplification, this can be written as 2 times the arctangent of 1 over the square root of phi, where phi is 1 plus radical 5 over 2, otherwise known as the golden ratio. And that's it. Our integral is equal to 4 pi times the arctan of 1 over the square root of the golden ratio. The most interesting integral in the world. And with that, thanks for watching.